Hello everyone, I am Luca Brighetti and I'm going to present you the project of the Group 5 which concerns the vibrations analysis of a 4-cylinder boxer engine. This is a quick summary of all the parts that will be covered into the presentation. Starting from the team overview, we have Federico, which is the coordinator, Daniele, which is the engine data analyst and provided the parameters of the engine to the other groups, such as the theoretical development group, which is made up by Alberto and Luca, and the numerical implementation group, composed by Eduardo and Enrico. The graphics are made by Davide. This is the workflow chart of our project. First, we understood the constraints of the problem, then we defined the speed ramp of the engine and its inertial forces. We modeled the mounting system and then we wrote the equations of motion. We solved them both in transient and in steady state conditions, and at the end we moved to the frequency domain. So the engine parameters are taken from the Subaru FA20 boxer engine. The weights are displayed in the first table. The dimensions are shown. There are also the overall dimensions and the inertia metrics developed through a suitable CAD model. We started with the inertial forces analysis. We considered a single cylinder engine first. So we wrote the displacements of the piston and the displacements of the conrod. And we used the MATLAB symbolic math toolbox to calculate the exact accelerations by using the diff function. At the end, we wrote the inertial forces, and we moved from the single cylinder to the 4-cylinder in the boxer configuration. Here, the inertial forces of each cylinder are plotted against the crankshaft speed. It is possible to see that the boxer engine is a very well-balanced configuration because the sum of these inertial forces is 0. So the only excitation that we have is a second-order yaw torque, which is plotted against the crankshaft speed as well. The analytical formulation is shown, and the quadratic trend is given by the term omega squared. So we used the simplified model of the engine shown in the picture. This is the equation of motion in the matrix form, and the mass matrix is displayed. The Cauchy problem is completed by adding the initial conditions. The stiffness matrix is made up by 4 sub-matrices, which are combinations of Ki matrix, which contains the stiffness coefficients of each engine mount, and Ri matrix, which contains the positions of the engine mount with respect to the coordinate system. We consider the free and damped problem to search for the modes of vibration. So the eigenvalue problem was solved with the eigen function in MATLAB. In the first table, the natural frequencies of the system are shown both in radian per second and in RPM. And in the second table, the model matrix is shown. It contains all the mode shapes. Okay, since that the real damping is difficult to be characterized, we considered the damping matrix proportional to both mass and stiffness matrices. This is called the Rayleigh proportional damping, and it is an approximation. So switching to model coordinates, and after a few mathematical passages, it is possible to obtain the governing equation for the harmonic oscillator, which solution is given by the convolution integral. So we used the ODE45 MATLAB function to double check the solution given by the convolution integral. Here, the displacements of the engine are shown. OD45 and convolution have got a perfect match between each other. It is possible to note that the displacements are higher for low RPM due to the resonances. In particular, we are focused on the bottom right graph, which is the rotation around the Z-axis, which is the main deflection of our system. Here, the accelerations of the engine are shown. The formula is obtained by inverting the equation of motion. At the end, we plotted the forces transmitted to the frame. It is possible to see that there is a peak of torque transmitted of 150 Newton meters. This leads to an uncomfortable perception for the driver, and we were not so satisfied with this result. This is why we decided to optimize the engine mounts. We set our boundary settings in terms of minimum stiffness, maximum stiffness, and maximum deflection of the engine. Then we defined an objective function, which is to minimize the forces transmitted. Okay, this is the algorithm that we used to solve the problem. And the algorithm provided some stiffness coefficients. The deflections are calculated, and if such deflections are inside the boundary, then we have finished. Otherwise, we have to repeat the cycle again. These are the displacements of the engine with the new stiffness coefficient. These are the accelerations with the new stiffness coefficients. And last, the forces transmitted. Now, the maximum torque is 10 Newton meter, which represents a 94% reduction compared to the previous case. There are small vibrations transmitted to the driver now, and we are satisfied with this result. Then, 3 regimes are investigated. The idle regime is a very common situation, for instance when you are stuck in the traffic or in front of the traffic light. Then we considered the resonance regime and the maximum regime in order to see which one of them have got higher vibrations. The methods used to solve the problem are the same discussed before. These are the displacements of the engine for the idle regime, the ones for the resonance regime, and the ones for the maximum regime. Then we have the accelerations. At the end, we have the forces transmitted for the idle regime, the resonance regime, and the maximum regime. So in the top of the slide, you can see that the torque transmitted at the idle regime is slightly higher than the other regimes. Anyway, its value is pretty low because we have already filtered the vibrations through the optimization of the engine mount. So we are moving to the end of the presentation. This is the Fourier transform of the displacements at the idle regime. This is for the resonance regime, and this is for the maximum regime. There is only a peak in correspondence to the second engine order, because we have got a second engine order excitation. In other words, if omega is the crankshaft speed, then the forces acting on the engine have a frequency of 2 times omega, and consequently the displacements of the engine have got a frequency of 2 times omega. There is also a little peak for low frequencies, which is a noisy contribute, a noisy term, given by one natural frequency, but it is negligible and it could be filtered. In conclusion, the Boxer engine is a very well balanced configuration. We decided to optimize the stiffness coefficient in order to reduce even more the vibrations to the frame, leading to a comfortable drive. In this way, the vibrations of the engine are almost imperceptible for the driver. These are the references that we used for our project, and I would like to thank you for the attention, and I hope you enjoyed our presentation.